So if you look in D2L, what you're going to see is, let me switch over to student mode. If you look under content, you'll see there's a folder there now called videos. And each lecture will be posted to videos. They are YouTube videos. I mean, yeah, they're on YouTube, but they're linked to in D2L. Once you go to that link, you can click on the name of it and actually view it in YouTube rather than in that D2L window, which is what I'd recommend. And I'm also building playlists for each class. So, you know, at a certain point, you may just, you know, bookmark a playlist or whatever and be able to follow it that way. But that's how you find them. Go to content, scroll down, go to, you know, video, click on the video, and then open it by clicking on the name of it right there. Unless you just want to watch it on this little preview, that's fine. However you like to do it. When you're following along at home, it's nice, right, to have two screens or a really wide screen or to have a, you know, a tablet sitting there that you can do. It's nice if you have that set up, but people do manage to watch a video and type the code in, you know, even without that situation. So our PowerPoints are over under content as well. You can choose content and go down and look under Unit 1. We should have several PowerPoints there, chapters 1, 2, 3, and 4. That consists of our first unit, and the exam will be over chapters 2, 3, and 4. I don't think there's anything in here that I want to talk about that I actually want to. If there is something from chapter 1 that I want you to have memorized for the exam, then I will let you know. And I'm pretty sure I've already mentioned this, but the exam is open book, so if it was the case that I asked you about something in chapter 1, you wouldn't need to panic. You could flip through the book and find it. Whenever you're in a preview window like this in D2L, it's always better to download it and view it separately. And that's particularly true of PowerPoints. This is like a 46-page document. D2L tries to do a good job of displaying it, but it's always better just to download it. So I'm going to go and download the chapter 1 PowerPoint. I said I'm going to go and download. There we go. And if you just want to watch the screen, that's fine. If you want to pop open the PowerPoint on your own, that's also totally cool. So why program? What is a computer? A computer is a programmable machine designed to follow instructions. You know, if you had a little handheld calculator, not one of those nice expensive ones, you know, your TI-90s or whatever. Is it a computer? Probably not. It's got a whole bunch of chips and stuff in it, but it doesn't follow instructions. You can't give it a series of instructions and have it figure it out for you. You have to type in what you want it to do. 1 plus 2 divided by 3 equals. You know, there's no program that you enter into it in order to get it to do something. That's what a program is. A program is instructions in computer memory to make it do something. And a programmer is a person who writes instructions to make computers perform a task. So without programmers, no programs. Without programs, a computer cannot do anything. Okay, so I'm going to diverge from this just briefly, and I'm going to write on the board, draw pictures, and we're going to talk about how a computer works on a certain level. And it's going to be incredibly simplified, but we're going to talk about the idea of a programmable machine designed to follow instructions. First thing I want to do is I want to show you some old-fashioned computers. Let's see, how about the difference engine? How's that, baby? That's a steam power computer. And honestly actually works. Although the guy who was inventing it in the 1800s, you know, he had a lot of grants from the British government and from companies who were interested in making things like that, and he never actually quite got to complete it. There were other people who were making simpler versions, you know, programmable calculators. Not programmable in the way that we think of it. But, you know, during the 1800s, that's when science was exploding and business was exploding, and the need to, you know, track figures and to add things up was becoming inordinately large. You know, the need was there, and people didn't really know how to handle it. So, for example, if you were plotting your course, you know, over the sea or whatever, you needed very exact tables. Well, you would buy a book that had tables of logarithms and other calculations already pre-solved in them. And so if you're a astronomer doing calculations, and well, Saturn ought to be at this particular angle, but I'm trying to figure out, its orbit around the sun, and I need to know these square roots and logarithms and stuff like that. They couldn't whip out their calculator and have that. So instead, they would work at, the university or whatever, where they had these tables full of figures, not only, books full of tables of figures, just like we have encyclopedias. And they'd go, okay, I need all the logarithms for the power of 17, and they'd go that and look at it, and then some poor guy, 30 years ago, had sat there performing calculation after calculation after calculation and writing them into the book. How boring would that have been? Okay, yeah, but at least he had employment until he finished that book. But then when you were looking at it, you had no idea whether he had any errors in it or not, right? Maybe the guy just wanted to get home early, so he started fudging, the numbers, and then he left early or whatever. So the idea is that if you had to have a book full of tables, mathematical calculations, figured out like to the 10th decimal point or something like that, you'd want it to be very precise. You'd want it to be very accurate. It'd be even neater if you could just do it on your desktop. But barring that, you could have something that would print out a series of tables, mathematical calculations. And I'll give an example of that kind of thing that these things could do. I never know if y'all can see or if the glare is too bright. I'm going to have to go and let me know. Can you see this if I write here? No, that's a lousy marker anyway. Maybe I should just turn off the light and go crank it up. I'll do that. I want a remote control. I'm going to make you my remote control. So suppose you had some polynomial equation like this. 3x squared plus 2x plus 10. And you were told, okay, I want you to write down the answers for this for all the values between 1 and 100. Okay, so here you pull out your abacus, or however clever Oxford students did in the 1800s, and you perform that calculation 100 times in a row, and you hope you got it right. If we look at it, we could probably figure out a pattern to these answers. I'm going to go ahead and try that. I'm going to fill this in for a few different numbers. I should have written that over there so I have more room to write up and down. This isn't a math class. You're not going to be expected to do this. 3x squared plus 2x plus 7. I think it was something like that. So let's solve it for 0. 0 squared plus 0 plus 7. Okay, so that's 7. Let's solve it for 1. 1 is 3x squared, so that's 3. Plus 2 more is 5. Plus 7 is 12. I think I'm getting that right. 2. 12 plus 4, 16, 23. We'll just do one more. 3. That's 9, 27. Did you say 40? All right, I'll go with it. So if we look at it, we can start measuring the differences between these. The difference between that one and that one is 5. I'm not sure that. No, it's not. Which one's wrong?
I think it's right.
All right, so 3 times 9 is 27 plus 6 is 33 plus 7 is 40. All right. I'm getting the feeling, though, that I've done something wrong here. The difference between those two is 11. The difference between those two, oh, it looks like I did it right, is 17. You can kind of see a pattern there, right? These are all like 6 apart. What's the difference between that one and that one? 6. The difference between that one and that one? 6. We can take a wild guess as to what the next one's going to be. we would just add 6 to that, and that becomes 23, and 23 plus 40 is 63. So if we plugged in 4 into our equation, we ought to get 63. 4 squared is 16 times 8 is 48, plus 8 is 50, 6 plus 7 is 63. Okay, and it worked. You see how these numbers fell into a very predictable pattern? Well, you could solve a whole bunch of these just by recognizing that pattern and writing them down. But even better, you could program, you could get something with wheels that you could set and then turn a crank, and it would do this math for you, so that you just have to write down the answer. You'd set down, the values for each of your coefficients or whatever they're called. I'm not quite remembering. And then you do it once, and it'd show you the answer for that. And you do it twice, and it'd show you the answer for that. You do it 3 times, you show you the answer for that. So one of the devices that could do that was. All right, Kathleen, let's try the remote control thing. Can you dim the lights? All righty. This Pascal's calculator. Now he did his in the 1700s, not the 1800s. We're going to have our lights on at some point, right? I'm impatient. Come on. There we go. All righty. And you can see we have these wheels that you spun, It had these numbers that showed up here. That's an actually pretty sophisticated piece of equipment to be milled for the 1700s, right? So, Pascal, I don't know if he made a lot of money. You may have heard the term Pascal. It's a programming language which was named after this. But, you had to sit there and, configure all this stuff. The idea behind that big old steam power monster that I was showing you here is that, is this really a computer? No, you can't program it. It's a very specified tool for solving equations. But that's all that it is. The idea behind this thing is that by the middle 1800s, people were already using punch cards. But the punch cards would control weaving in looms, And so this guy came up with the idea, Charles Babbage was his name, of making a machine where you could tell it what to do by inserting punch cards into it, and then it could run, and then it would print its output in the form of punch cards. Sounds like a modern old-fashioned computer. So that's what this was, is it had input in the form of punch cards, and then it had the ability to perform those calculations, and then it had the ability to stamp punch cards on the way back out. And so this is called an analytical engine. And so the big deal about it was that you just didn't have certain wheels that you could, spin and then perform a single form of calculation. You would actually, with the punch cards that you gave it, instruct it in what form of calculations to do. And so that was the actual first programmable computer. Except, unfortunately, he didn't quite get it to finish because the precision required to mill these pieces of metal was extraordinarily. He needed, very, very precise milling, and it was very, very expensive. And eventually, his backers and the government of Britain, withdrew their funding or whatever, and so he never got to finish it. But the idea totally works, and people have built them, in order to prove that they work. And he communicated his ideas with somebody else named Ada Lovelace, and she was essentially the first programmer because she would document what this was and how the programming of it was going to work, what you would have to put on the punch cards in order to get it to perform calculations and to produce output. And so from her notes, that was the first programming language in effect. And it's pretty cool that all that stuff happened in the 1800s. The genre of science fiction now called steampunk. I'm sure that, some of y'all have seen that. It pretty much came up when one of the cyberpunk authors named Bruce Sterling cooperated with another one, and I've forgotten his name, and they wrote a book called The Difference Engine. And the idea was, what if the 1800s they really had invented working computers, and so the cyber revolution had taken place, a century and a half earlier than it did in our world. So anyways, that's our computer. Let's go back and hit our PowerPoint. A computer is a programmable machine designed to follow instructions. I was going to sit up there and draw pictures about a man in a box, but I think I'll wait. Program is the instructions that make it do something. The programmer is the guy who writes, not the guy. That is incredibly sexist. When I went to school in the 80s, getting my comp-sci degrees, it was very strange because the classes were about 50-50 distributed between men and women. And then nowadays, you know, I come into a class and usually it's like 25-75, and I don't know why it happened. It's not like, you know, why did it happen? I have no idea. But if I ever use the term guys, it's meant to apply to everybody, regardless of any gender. So without programmers, no programs. Without programs, the computer can't do anything. I might have to get there and draw pictures. The central processing unit, main memory, secondary memory, input devices, output devices. Yeah, unfortunately, I do want to draw more pictures, so I'm going to ask Kathleen to hit the lights again. This is cool. I've never actually had a remote control in the classroom. So, what is a computer? It's a little man in a box called Chip. That's his name. Okay, that's my joke. So, Chip is a guy who's locked in a box, but he's got little armholes so he can reach out of it. He's got a crayon for writing, and he's got an extraordinarily long piece of paper. It might be 1 billion lines long, might be 5 billion lines long. You know, that's what giga means when you're buying a computer and it says it has 8 gigabytes of RAM. Giga means billion. So maybe he has 1 billion different places that he could write. Each line has enough room to write one number. And we're just going to number those 1, 2, 3, 4, 5, 6, 7, 8, right, like that. So he can look out his box and he can write and erase and, you know, read from that extraordinarily long piece of paper, which we're going to call memory. Why is it memory? Because even once he leaves, he can come back the next day, that data is still there. It has been remembered. So Chip is our central processing unit, CPU. We tell Chip what to do with instructions. We might come up with a language that Chip understands. We might say that we have some commands for him to follow. And he's only going to have 3 or 4 commands that he needs to do. I1 is going to be a read. I2 is going to be a write. And I3 is going to be an add. So right now, he only has a vocabulary of 3 words. Along with his memory there, he's got a little place inside the box where he can write figures down temporarily real quickly, like you have, you know, a sticky pad or whatever. You write something temporarily, you can throw it away when you're done with it, whatever. These are registers, register 1, register 2, register 3. They're just temporary places that are inside the chip so that they can be written to and accessed very, very quickly, right? Because here he'd have to open the window and he'd have to scroll the paper to the right place. It takes a long time for him, like if you told him to get to address 1 million. You know, but these are right there with him. He can get them really quick. And I know that some of y'all know way more about this than I am, and you're allowed to laugh and sneer at my little parable here. So anyways, we're going to give him some commands. We're going to say, I1 from address 4 to register 1. That's our command. And then I1 from address 3 to register 2. And then I3, R1, R2, R3. And then we're going to give him one last more command, which is I2, R3, address 6. All right, does that sound like it means anything? No, but we're going to follow these in order. I1, what does I1 mean? It means read from address 4 and stored in register 1. Okay, now I don't actually have any data here, right? So I'm going to just write some numbers in. That's a 2, that's a 30, that's a 7. I'm totally making these up. 6, 9, 0, 55, 4, 11, whatever. Okay, so I1, read from address 3, read from address 4 and stored in R1. Read address 4, stored in R1. Okay, address 4's got a 6. He's done that command, he's done with it. His next instruction, I1, which means read from address 3 and write it to R2. So what's in address 3, if you can read my writing? Yeah, it's a 12. Okay, so he's done that. He did that command. And then I3, which stands for add. Add what's in register 1 to register 2 and store it in register 3. So register 1's got a 6, register 2's got a 12. He adds them, and he writes the result down in register 3. He's done that command. And his last command, I2, which is write what's in R3 back out into address 6. So we have an 18 here. He would go and he would erase that and put an 18 there. So he has done that. He had these instructions. He followed our instructions to the letter in order to do that. Now these commands here are technically what are known as opcodes, operation codes. And each chip has its own set of opcodes, different brands or whatever. And is this a realistic list of opcodes, 3 of them? No, nowadays, the processors are so complicated and geared for speed and whatever that they have hundreds upon hundreds of opcodes. And so, chips are very, very complicated. What we described here is more like 1940s technology. But the 1940s is when the first electronic computers were invented. Maybe we'll show a picture of them as we go along. So we gave him some instructions in a series of opcodes. Now for this to be a more realistic thing, where did he get these instructions from? Did we just throw note cards into his box and get him to do it? No, these instructions were also written as part of the memory. So say at memory address 1000, this information was written out. Those 4 lines of code were written out down there. And so what we would really do is we come and we kick Chip and say, okay, start running from address 1000. And so he'd look at 1000, which was that one, and he'd do it. And then he'd look at, the next one and do it. And he'd do that one, and he'd do that one. And there ought to be a stop or something that tells him to stop. So that's what our CPU is doing. He's getting instructions, and he's reading from memory. He's doing math, and he's writing to memory. Now, what if it's more complicated than that, which it always is, right? What if he needs to, he needs to display an image on this screen? What does another do in another box? And he's sitting inside a video card. And so this guy is writing data in such a way that he can read it. Maybe they're reading from the same RAM. Back in the old days, you had video cards that didn't have their own RAM. They shared the memory with the main processor unit, which was very slow. So, that would mean he was writing his stuff out to here, and then when he wanted to draw from it, he would read that data from there. They were all reading from the same memory. It could only be done half as fast, and so those video cards are slow. Nowadays, video cards have their own RAM in them, right? So he could be sending signals to him, I want you to do that, and it would be up to him to decide what the picture will look like, and then just dump that to display or something like that. So nowadays, every component is a computer. Your keyboard is a computer unto itself. Your mouse has, computer processing in it as well. But in general, the act of reading something in, like say we have a keyboard here. You type on the keyboard, and a bunch of impulses, a bunch of numbers representing letters and stuff like that is eventually written to memory so that he can read it. So that's called input. Input is taking something external to the system and recording it in memory so that he can then do something with it. So an input device is something like a keyboard or a mouse. And then a display is something like, another thing that reads from the memory and then goes and sends data out, like a printer, a display. A speaker, a speaker is, a form of output. So output is when you're getting things out of the computer and sending it, somewhere else. And then there are communication devices, which is where somebody's output is somebody else's input, and vice versa. You have two-way communication between two computers. Alrighty. Sorry, Chip, we're going to cover you up again. Lights, please. Thank you. Alrighty. So nowadays, the computer that you use the most is your phone. It's everything. It's got a processing unit. It's got, an input screen that also serves as its input and the output and everything. But anyways, so all these books are written like, what computers look like in the 80s or the 90s. Here's your input devices. Things that send signals into the computer. Cameras, keyboards, joysticks, whatever. Then you have what's known as a secondary storage device. And I should have written this on the board while we had Chip up there. What if Chip's paper disappeared? It got burned up every time we turned the computer on. That's the case. That's what's known as dynamic RAM. It maintains its information only as long as there's power to it. And that's not too good. You could sit there typing in, your master's thesis, and it's sitting there in the memory of the computer, but then you accidentally unplug your computer and all the memory's gone and all gets reset back to zero. That's not too cool. So you have what are known as secondary storage devices, which are meant to be semi-permanent. This data in these secondary storage devices maintains itself even without any power. Like your little SD cards, right? You stick your card inside your old PlayStation or your camera or whatever. It doesn't always have to have power to it. You can pop it out and put it back in later. Our USB drives, are like that. Until, the last 10, 15 years, secondary storage devices were based on the idea of spinning platters of something, with magnetic coating on it. If it was only for reading, it would spin, an aluminum disc, a CD, that had pits burned into it or whatever. But those were read-only, and then they came out with CD-ROM drives. ROM means read-only those, so they won't only CD-ROM, they were RW. You probably had one of those. You could burn your own CDs back when you were a kid, So anyways, a secondary storage device is one where you write the contents of the RAM and store it somewhere so that when you turn your computer off, or if you take this thing elsewhere, you can load it back in. And so secondary storage is used for data, and it's also used to hold the applications that run the computer. And the same distinctions are even in your phones. There is memory inside your phone that gets reset if you do the reboot thing, you force the button down and it turns the phone off or whatever, or your battery runs out. And then there's, a more permanent form of storage in it, flash RAM. So central processing unit, that's the control unit. It retrieves and decodes program instructions. What do I mean by retrieve and program? We had that memory, that piece of paper. He had to have the ability to pull those instructions out so that he could do stuff. He retrieves the instructions and he decodes them. What does that mean? Well, they're just a series of numbers. That's all that a computer can handle ultimately is a series of numbers. And it's up to the chip to decide what kind of number means what. Is this an opcode? And then it's up to the program, really, to determine whether this number means the letter A or the letter B or whether it's part of a musical file or whatever. The CPU is getting a series of instructions. It coordinates activities of all the other parts of the computer. So the man in this box is talking to, that hard drive and to that display and stuff like that. Then he's got a buddy who's incredibly good at math. And so we put another box next to him, and that's an arithmetic and logic unit. Optimized for high-speed numeric calculations. Nowadays, those are just baked into the chips. You don't install a separate, arithmetic card into your computer in order to be able to do this stuff. It's just all built into the chip. You have one chip that contains all of this stuff. They're called SoC, System on a Chip, where you have absolutely everything that you need for a computer on one chip, which is why they can make those Raspberry Pis, those computers that, are hardly as big as a cigarette box, and yet they're an entire computer. So main memory is volatile. That means it's going to fly off the handle. No, I'm kidding. What it means is it's erased when the program terminates or the computer is turned off. There's a movie called Stand By Me, which some of y'all may have seen. It's from a Stephen King story. And during the entire movie, the framing device for the movie is that this guy is writing his life story, and then they go back, and the whole movie really is a life story of a kid. And then it comes back out, and in the very last, 45 seconds is the grown-up guy, and he's done writing his story. And he's been doing it on a word processor on a computer, and so he's finished, and he turns his computer off. I didn't see you hit the save button. You've lost your entire story. Okay, anyways, it aggravated me. So that's a problem. Your main memory is erased when the program terminates. It's called random access memory. Could you have a form of non-volatile random access memory? Yeah, they played with that for a while, but they never got it to be very fast. It was called bubble memory. There's all sorts of things that you can use to store values. Back before we had our awesome little chips and memory cards and stuff like that. I talked about the first electronic computers from the 40s.
During World War II?
Yeah, during World War II. And there's an incredible movie about...
Wasn't it called The Imitation Game?
Yep, that's it. Yeah. So, old computers. Come back. I just want the pictures. I don't want anything else. All right, how would you like that on your desktop in order to play, Call of Duty or something like that? The way you programmed these beasts is by hooking up patch cables from device to the device, just like a telephone operator, except you had to know what parts of the machine you were wiring together to do it. And it's kind of odd, but yeah, as in that movie. By and large, the first computer programmers were largely women. They were PhDs, teachers and stuff like that, math professors who were, drafted into the war effort to work on these things. And so they learned how to program. And quite often, all they had was the mechanical specifications of it. And just like Ada Lovelace in the 1800s, they would be the ones to actually figure out how to make it do things. And so you had this weird disparity of you had the guy engineers who would build the boxes, and then you had the women who would figure out how to make the boxes do things. But then whenever you had pictures of them posted in Life magazine or whatever, it was always a guy there. So I've already forgotten the name of the movie. I'm totally bad. Tell me the name.
Imitation Game.
Imitation Game.
Alan Turing.
That's one of the ones that I love. And then there's another one that if it comes to me, I'd highly recommend that y'all watch.
Is it Hidden Figures?
Hidden Figures. That's the other one. I love the Hidden Figures movie. I ought to give y'all extra credit if you watch Hidden Figures. It's totally cool. And both of these are true stories, actually. The Imitation Game about Alan Turing. Alan Turing is pretty much the father of modern computing. The English and the Americans use computers for two different purposes, really. The Americans wanted to build better weapons and nuclear bombs and stuff like that. So their computers were used for performing the calculations for weapons research and to create tables, that your bombardiers could use to, calibrate their things the right way, or to send this shell, a mile and a half that way with this wind speed and with this load, or to hit the enemy ship or whatever. You had to have these tables. And so the Americans wanted a very fast way of creating these tables to use in the weapons efforts, while the British used them to crack codes, like the Enigma code, the one that the Germans were using. And so they needed to invent devices that could do that because the Enigma code was extraordinarily hard. And Alan Turing was the guy in England who kind of led that effort. And pretty much you hear the term Turing machine or the Turing test. If you go on in this career and do reading about the history of programming, you're going to see Alan Turing's name all over it. And that's what that book, that's what The Imitation Game movie is about. I'm gonna ask you all to do that. Just Imitation Game or Hidden Figures. I strongly recommend y'all go watch these. Okay. Anyways. Memory is organized like this. Ultimately, all you can have are zeros and ones. Either something is on or something is off. Before even vacuum tubes, you had, electric relays where if, the relay was closed, current was flowing through, and then if you broke the relay was open, then it was off. I was going somewhere with that. Nicholas Tesla did stuff that created circuits that are still in use inside computers in the form of NAND gates, and the logic of them and the relays closing them. Anyways, so zeros and ones, that's all that ultimately a computer does. It's a transistor that has a certain amount of power in it, and that represents a zero, and another amount that has a one. Or it's a magnetic platter where if it's got signal here, it's a zero or it's a one. And these are grouped together by our convention. Didn't have to be. On another planet they would be different. So that 8 of those bits, which are zeros and ones, turn into one number called a byte. And we'll get back to that, but I don't want to talk about that right now. So your main memory, every line on that scrolling piece of paper I talked about, every number, every byte has its address. And so here's an example of some memory. We have a 30-byte computer. And in it, in the 16th byte is written a number. And in the 23rd byte is written another number. So secondary storage is non-volatile. It's data that's returned, that is retained. It's not erased just because you interrupted power to it. Variety of media, magnetic, your old floppy disks, your hard drives, optical, your CD-ROMs, your DVDs, your flash drives. So the big thing recently in the past decade or so has been moving away from the spinning devices. And that's why, your cool laptops, your speedy ones come with the solid state hard drive rather than the spinning one. And they're so much faster than, than the spinning hard drives that you buy. And the solid state hard drives cost a little more, but they use less power, and they're faster, and so people like them. Input devices send information from the outside world into the computer. Lots of things can be input. All of our programming is pretty much going to take the form of writing an application where you type data into it and then it prints data back out. That's really all it's going to be. Kind of, old school people were used to write programs, typing in things on and having the actual be printed like on a good old typewriter or teletype machine. They're still going to be doing that kind of stuff. That's how you learn. You start with those building blocks and then you get larger. The programmer is the software differentiated from hardware. Hardware is the stuff you can pick up. Software is the stuff that you can't pick up because it's symbols. Software are the instructions that run the computer. You can have all sorts of different software. There's operating systems, utility programs, software development tools. So when we launch Visual Studio, we're launching a software development tool. What's a utility program? Well, a utility program is something like if you have to reformat your drive, or you need to go and adjust your resolution or something like that. That's that. Operating system, that's what your computer comes with, and it just, those are the programs that actually let the computer live and breathe, and Windows is this thing's operating system. Then there are applications. They don't mention that, but applications are things that an end user runs, not for managing the computer itself. That's a utility, but in order to make money or have fun. Application software, programs that provide services to the users. Word processing, like Word. Programs to solve specific problems. Games. Programs and programming languages. The program is a set of instructions that the computer follows to perform a task. We start with an algorithm, which is a set of well-defined steps. An algorithm for calculating pay. This is written in plain English. Display a method on the screen asking how many hours did you work. Wait for the user to enter the number of hours worked. Once the user enters a number, store it in memory. Display a message on the screen asking how much did you get paid per hour. You wait for the user to type in an hourly pay rate. Once the user enters the number stored in memory, then multiply the number of hours by the amount paid per hour and store the result in memory. And then display a message on the screen that tells the amount of money earned. The message must include the result of the calculation performed in step 5. Okay, so an algorithm is just an English, or whatever language it was written in, description of a process to solve a problem. A recipe is an algorithm. You know, take 2 eggs, 4 pounds of butter, and 30 cups of nutmeg. Put in bowl, stick in microwave, throw away. Okay, there's my recipe, but that's an algorithm. Why don't we stop the onslaught of lecturing and actually write a program that does this? So we're going to launch Visual Studio so that we can do this. So I'm going to go down here in this search box. I'm going to type VIS, and it's going to find Visual Studio. And by the way, somebody texted me, and I'm sorry I haven't responded yet, which version of Visual Studio to get. There are like 27 different versions of it, and all of them work. So I would just get the newest one and roll with it.
First problem I had was, do they take community or enterprise?
Either one would work. Yeah. Yeah. So I'm going to launch Visual Studio, and then not only that, once the icon shows up down here, I'm going to dock it to the, right click, pin this program to taskbar so that I can get to it again really easily. All right, so this is Visual Studio. It's known as an integrated development environment. Back in the old days, you didn't have a nice application that would let you enter your program, enter your data, run the program, debug it. Instead, you did everything from a command prompt. Don't type this, but you would launch an editor, then you would save your file, and then you would run another program that would compile that file, and then you would run another program that would link that file, and then you would finally run that program. Yeah, but this does all of that. So we're going to make a C++ program. It's a series of steps we need to follow that I should actually put down on paper so that you could follow these at home, but hopefully you'll remember them. New project. And there's 27 different kinds of projects, or 27,000. We want Visual C++. But more specifically, we want an empty project. I'm not even sure which one that's under. On this one, it's under General. But if you click on Visual C++, you'll see empty project. That's what we want. Let's give it a name. I tend to just name them by the day, January 25. Look here. Look at this location of where it is being stored. You're going to have to remember that so that when you want to upload your into the Dropbox, you're going to have to be able to find that project. You know what I'm going to do is I'm just going to copy that entire line right there and stick it in Notepad so I can get it later. Do you have to do that? No. But I just kind of like keeping that there for a little while so that when I actually go and need to upload it, I know where I can find it. All right, now I'm going to click OK. Now I'm going to click OK. What is it yelling at me about?
Yeah, mine's doing that too.
Thank you.
Do you need another slash after projects?
Maybe that directory is write protected. I'm going to try moving my project directory. So what I'm doing is I should actually do it first to make sure it works. But I'm clicking Browse, and I'm going to go into Documents. I'm going to make a new folder inside Documents called Visual Studio Projects. And then I'm going to double click that. Where'd it go? Right there. And that's where I'm going to save my projects.
Okay, there it goes.
Select folder. Let's see if that works. And yeah, you're right. Maybe it was the absence of the final slash. Okay, it would have been nice if it had actually given us an error message rather than just flickering like that. All right. So it created the project, but it didn't actually create any files other than the project files. It didn't create any programming files. Let me go show you what it did make. Let's see, I said these were stored in documents, Visual Studio projects. There's my Jan 25 file folder. We see all these things in here. Do yours have extensions like .sln and .sdf? That's useful information. If you don't see those extensions, you should turn them on. And the way you do that in this version of Windows is you go to Organize, Folder, and Search Options. So all I did is I popped open, a copy of the Windows Explorer, not the Internet Explorer, and then chose Organize, Folder, and Search Options. Go to View, and where it says Hide Extensions, you don't want that selected. Deselect Hide Extensions and click OK. That way you can. Those extensions are very useful information. You may wind up with 20 files with the same name and they only differ by their extensions. You have .exe and .cpp, which stands for C++, and so on. Okay, so if I poke around here, I don't actually have any programming files. These are the project files. These are the files that Visual Studio uses to keep track of your project, but we don't have any programming code in it. That's what we're going to do now. I'm going to go to Source Files. Back inside Visual Studio, is everybody here? Did everybody get a project made? Please don't let me get past this point because you won't be able to do the next step if you don't have it. Alright, so we're all good. Sometimes I have people who are too shy to ask for help, and then 20 minutes later they haven't gotten to do a thing because they didn't get past step 3 or whatever. And I don't blame them, but it just is not good for them. Okay, so add new item. Right click on source files, choose add new item. And what do we want? We want a C++ file. We could leave the name source.cpp. I will always accept that, but it'd be better to give it a better name than that. Why don't we call this payroll? And then click Add. All right, and now we actually have a programming file that we are creating that has a .cpp file extension. If we went back out into Explorer and we opened up Documents, found that folder, you don't have to do this. I should see that .cpp file there. That's what you're going to want to upload when we're done. If you can't find it, you should be able to right-click on the folder, on the project right here, and say Open Folder in File Explorer. So if you ever get lost and you can't find your CPP file, click on the top of the so-called solution. Sometimes Visual Studio calls it a project, sometimes they call it a solution. Here they're calling it a solution. You right-click on it, do Open Folder in File Explorer, and you'll be able to find your CPP file. Is it right there? No, but it's in the subdirectory of the same name. So let's write some code. Unfortunately, at this point, you're just going to be typing along with what I'm typing, right? So type in # or hashtag include IO stream, input output stream. Now we're going to add another line of text using namespace std, semicolon. All of this stuff will just be setting our program up so that it will understand what we're typing underneath it. Int main, parentheses, end parentheses. And on the next line, I'm putting a open curly brace, and on the line underneath that, I'm putting a closing curly brace. Some people like to put don't like putting the opening close curly brace on its own line. They leave it there. But I like doing it that way. So what are we going to do now? That payroll program needed 2 bits of information from the user. It needed to know their hours worked and their pay rate. So we're going to create 2 variables for storing those things. And by the way, you guys who came here from Python, in this language, tabbing is no longer the end-all be-all. It's still nice to tab stuff, but it's not essential. What's essential now to denote your logic clustering is the braces. So here we go. Let's declare 2 variables. We're going to call, we want them to be floating point so that they can say, I earn $3.75 an hour. Well, hopefully they earn more than that, but anyways. So we want a floating point rather than an int. If it was going to be a whole number, I would store it in a variable type known as int. So anyways, let's do that. Float.
Why doesn't it say int main when, what's int there mean?
What the int there means is what number it's going to return to the operating system when the operating system is done running. And we're just going to return a 0 every single time, but we still have to declare it as having a type. There are more than one types. We'll delete that one though. So we want hours, float hours, and we want float rate. That's how much you earn per hour. Now we want to ask the user for this information. And this looks different for you Java folk or your C# folk. See out how many hours did you work? Question mark. And after the end quote, I'm going to put 2 more of those less than signs, arrow, arrow, ENDL. That's an L, not a 1. That means end of line. All right. We've told them what we want them to do. They want to enter a number of hours, so we have to let us do some input. Out stands for console output. We're displaying information to the screen. Now we're going to read in information. So CIN greater than hours, semicolon. Now in this language, almost every line ends in a semicolon, which again is different from your Python users where you didn't use that. It didn't break Python if you put semicolons most of the time, but here we got to. It's how the C language knows the difference between one command and the next. All right, now we're going to do the same thing. We're going to ask them for their pay rate. Cout less than. What do you make per hour? End quote, less than, ENDL. And let's read in what they type in into the other variable, rate. All right, now that algorithm said to multiply those 2 values together to calculate their paycheck. They probably had a better term for that. Let me go see what they had. Whoopsie. Varzola. Store the result in memory. Earned. I guess we'll just call it earned. But we don't have a variable named earn yet, or earnings. So float earnings, and then earnings is equal to rate times hours. And then let's print that out. Cout less than. You earned let's go ahead and put a $sign followed by our end quote less than earnings less than ENDL. Now there's 2 more lines to the program we need to add. I'm trying to keep it all on one screen. I'm making the text a little bit smaller as I go along, but I need you guys in the back to tell me if I'm reducing the size too much. Okay, so the last thing we're going to do is we're going to make the computer pause. Tell you what, just put 2 little arrows, 2 little lines there. We're going to note that that's where we're going to put the pause, because I want you to see what it looks like if we don't have the pause there. And then underneath that, we're going to put the little word return 0. Now the C programming language was written back when everything was command prompt. You didn't have any windowed programs. So when one program would run, one program could call another one, and then that one could perform a calculation, and then it could return a value back. So if some other program called ours, we would be returning a 0 to it. That 0 is just being returned to the operating system. It's not going anywhere. But we have to follow the syntax. All right, now we're going to run it. I'm going to click Build, Rebuild Solution. That compiles it. It turns all this English text into machine language, object code. And if it doesn't say succeeded, then it means that there's a syntax error. Syntax error is a typo. Like, what if I forgot a semicolon somewhere because I was too used to Python? And then I tried to build it, rebuild solution. It says rebuild failed. Thankfully, it's underlining it. This is a lot easier to follow than idle was. You guys who use PyCharm, maybe PyCharm was better at finding syntax errors than idle was. But anyways, okay, so I'm going to build it. And then just to demonstrate this, I'm going to run it now. I'm going to click that green arrow, which is the same as start debugging. All right, it says how many hours did I work? I worked 40 hours. What do I make per hour? 9. Oh man, I didn't even get to see my results. So we need to stick a pause in there. And there's more than one way of doing this. This is a platform-specific way of doing that you Mac users will not want to do, is to put a system call in there. So system, parentheses, double quote. And by the way, these are all double quotes. In Python, it didn't matter which quotes you use. In this language, it does. And we're going to use the word pause, like that. End quote, end semicolon, like that. Or end quote, end parentheses, semicolon. Now when I run it, how many hours did you work? 40. What do I make per hour? 9. You earned 360. Press any key to continue. That's what that pause did. You could even see that yourself if you went out to a command prompt and typed pause. It would say press any key to continue. Now, you Mac users don't have to do that. Xcode does not close the window. If you wanted to embed a different kind of pause than that, you could do so. I guess I'll demonstrate it and then recommend that people just go ahead and stick with pause because it's easy. But you could do this. C out, press enter, or done, press enter, something like that. And then we'd have to use CIN to store into something. I'm just going to delete all that. That's too much trouble. Let's hang with using pause. The Mac users can leave that out. And so I want to wander around and make sure that this is working for all of y'all. I also want to create a Dropbox so that for those of y'all who've already gotten it working, because this is the last thing we're going to do in class today. We're about out of time. All right, if you refresh your assignments folder, you should see payroll. That's where I want you to upload your .cpp file. If you can't find your CPP file, remember what I said. Inside Visual Studio, if you click on the top line here where it says solution and do add or open file, open folder in File Explorer, you can find it that way. And you can use drag and drop to submit it. Okay, want to wander around and make sure everybody got this working. If you did and you upload the CPP file, you're done.
What was it after? Like Dropbox?
Yeah, it's assignments, and then it's the one that says in class A payroll. Normally I'll put the dates by them, I just hadn't done that yet. I'll do it now.
I can't see.
All right, so the folder has today's due date. It's not like you won't get any credit if you weren't here today to do it. You just watch the video that matched that date and then type what we do and then upload it into that. So if you ever have to miss a day, just do it that way.
The double slashes, I had comments.
Yeah. I should have mentioned what I was going to do with slashes. 2 slashes is a comment, just like hash is in a Python.
No, I can't upload this.
That's all good. So,
Why can't it upload?
Wait till we
I was looking for my computer button on the desktop.
No, I'll have to open something only, not many of you.
Just add the comments in. What's wrong with yours? That's a 1, not no. That N? Is that a 1 or an L? I mean, 1. Put an L. L. Yeah. It's supposed to stay for N line. Yeah, that was probably is. No, click that. If you click that play button, I think it will ask you for the results. Click that play button. Hey, there we go.
Get this up. I don't know how to get this.
Oh, that kind of broke out, didn't it? Well, tell you what, I'm going to come over here. Stand by you. We want that docked back in there. I don't want to get that loading. Where's Mr. Mouse? So anyways, what we want to do is we want to find that file. So I'm just going to come up here, right click, do open in File Explorer. Our CPP file.
It should be saved. When you built it,
So there we go. That's what we're going to upload. So then you can go into D12.
wherever you're saving, you should right
Alright,
click your source file.
here. Yeah, so that's what you're going to do.
For my homework, I may have to. I'll have to get used to doing this.
Yeah.
Oh, open folder and file.
With my computer.
There it is.
Thank
Can
God
you
I
upload
just
that payroll
upload.
to see?
Oh, yeah, stop letting us do this. Drag and drop.
All 9 plus Windows. Okay, we're good to go.
I think hopefully I have this problem on my computer at home. No, I do it.
Well, we have to find out where that file is, right? Okay, we open the folder so we can see it's stored in this path, Visual Studio Projects. Right now, I don't think it's one of those.
I hope that's it.
My documents, Visual Studio Projects. We ought to just dock this. Go there, we'll find our CPC. All right, there we go. And submit. How you doing? Oh, cool deal. So you just toss it in your next dash to upload it.
Alright, let's see if I can.
Now you're good. You're good. Cool deal.
That's all we're doing.
Yep, we're done for today.